Hello everyone. In the previous lecture, I talked about the first class of objects in R, that is vectors, and today we are going to discuss another class of object in R, which is arrays and matrices. So we'll see how to handle arrays and matrices in R. First of all, what are arrays? So basically arrays are multi-dimensional objects containing only one type of elements, that is either characters or numbers. And if we think about vectors, there also we talked about the same property, that is vectors contain only one kind of elements. Either all elements can be numeric or all elements can be characters. So arrays are similar in that manner. The difference is that arrays are basically multi-dimensional. That is, there are two or more than two dimensions in an array. So it can be considered as collection of vectors. So vector can be actually considered as a one-dimensional array, right? So our discussion will be similar to how we went about with discussing vector, but obviously now since we are dealing with multi-dimension, we'll have to learn how to define arrays and how to index arrays and how to apply certain functions on arrays. So first let us see what are the methods of creating arrays or defining arrays in R. So there is a function called array. This is an inbuilt function, and this function can be used to define or create an array in R, and it can be used to create either a numeric array or even a character array in R. So for example, here as you can see, in the arguments of the function array, the first argument will be the collection of elements which we want to assign to the array. So suppose here we want to define a character array. So here the elements are A, B, C, D, E and F, that is 6 elements, and then we have to define the dimensions of the array. So this second argument dim is for dimensions, or dimension of the array. So here if I define C23, you remember the C function is nothing but your concatenate function. Whenever we define an array, we use concatenate function. So here 2, 3 means that we are trying to define an array where the first dimension has size 2 and the second dimension has size 3. So we are defining a two-dimensional array here having 6 elements, 3 into 2 or 2 into 3, that is total 6 elements. So this is the arrangement we get. So basically when we use arrays or matrices, we are trying to arrange our data in a particular form which will be useful for us in different kinds of calculations, right? So here the arrangement we see, so we have defined the dimension as 2, 3. By default, it takes 2 rows and 3 columns. So the first dimension is the size of the rows, that is 2 rows, and the second dimension 3 is the size of the columns, that is there are 3 columns. And if we look at the assignment of these elements to these rows and columns, we can see that by default this function assigns the elements column wise. That is, the first column has been filled, A, B, then the second column has been filled, C, D, and then the third column has been filled, E, F. So by default, when we use the function array, the elements of the array are assigned column wise, right? And similarly, if we look at the second example here where we are creating a numeric array, and we have defined the size of the array or dimensions of the array as 3, 4, that is we are going for 3 rows and 4 columns. And here, so total number of elements obviously will be 3 into 4, that is 12. So either you can define the elements as a vector inside this array function, or what you can do is, if you already have defined a vector earlier, suppose I have defined a vector x here which has all the elements I want to be there in the array, then I can simply write the name of the vector here as x. So either you can define the vector inside the function array, or you can predefine the vector as you wish. And then you define the dimension of the array. So here again we are creating a two-dimensional array, right? Where the size of rows is 3 and size of columns is 4. So 4 columns and 3 rows. Again, you can see the assignment of these elements has been done column wise, that is 1 2 3 has been assigned to the first column, then the next 3 4 5 6 assigned to the second column, and so on. So column wise assignment has been made. So let's see how it looks in R. If we want to create it, let's create the array x nn there, because we'll be using it for further calculations. Yeah. So let us use the script file here. Suppose I'm defining a vector x. We need 12. So let us define and then give any name to the array as array, then x comma dimension, say 3 comma 4, right? So if we run it, you can run the selection once or run it 2 arguments. Okay, 1 2 3 dimension equal to c comma 4. Sorry for that, I missed it. So I run it again. Yeah. So now if you look at what values have been entered in this array, you can see this is the output. And just give a look at this notation which we have arrived at. You know, this is helpful because this is how we index in arrays or matrices. So the first column has been denoted by blank comma 1. So it means first column and all the rows. This means blank means all rows. So all rows and first column. So these are the values of the first column. Similarly, you can represent the second column, all values of the second column, or the vector of the second column as simply this, and so on, comma 3 and comma 4. So basically blank means all the values in second column, all the values in third column, and so on. And similarly, if we look at the notation for the rows, it says, because the first dimension is for row, so first means first row, and then comma blank represents all values in the first row, that is the vector of the first row. So this is 1 comma blank, and so on, right? And similarly, actually, since we defined array having multiple dimensions, so we can have arrays having more than 2 dimensions as well, and it is very commonly used. So suppose we want to define an array which has 3 dimensions, then we have to make sure that while defining the dimension, we gave the size of each dimension as we pass it as an argument in the function array. So suppose we define this new array right? So suppose I define y as containing the values 1 to 24. The sequence, we are creating a sequence here, right, using colon sign, and then we create an array like this, y comma dimension is equal to, now we want 3 dimensions, so suppose 2, 3 and 4, right? So if we run these statements, let's see what happens, and we see what is saved in M. You see, so we have 3 dimensions, defined 3 dimensions. There were 24 values in all, 2 into 3 into 4, that is 24. The first dimension has size 2, that is, it has 2 levels. The second dimension has 3 levels, and the third dimension has 4 levels. The third dimension has been denoted like this. You see, blank, comma, 1. That means all values in the first dimension, all values in the second dimension for the first level of the third dimension. This is what it means. And then within that, all values of the first and second dimensions have been given like this. So this entire thing is a kind of 2-dimensional array within one level of the third dimension. This is how you can understand, right? So sometimes it becomes difficult to understand if you are not from a mathematics background, but soon you'll be when you use it, you'll be able to comprehend it very clearly. So just understand that this remains the same, because in 2 dimensions we could easily say which is the row, which is the column. So this is how we represent the 2 dimension: first row, second row, then first column, second column, third column. And then when we add a third dimension, that means we can consider it as a combination of 2-dimensional arrays. And so this is the first level of the third dimension, this is the second level of the third dimension, this is the third level of the third dimension, and this is the fourth level of the third dimension. So this is how it can be represented, right? So there can be even more number of dimensions in an array, but obviously it becomes very complicated to understand it. But when we are using it regularly, we can easily comprehend how it functions. So the nature of indexing actually remains the same, whether we are using 2 dimensions or 3 dimensions or 4 dimensions or any number of dimensions in arrays. So this tells us that yes, we can use more than 2 dimensions in arrays. And next, so the important question is how to do indexing in arrays, because we know that for mathematical calculations it is very important. We learned indexing of vectors in the previous lecture, and here we should first understand that we are moving ahead with the same concept which we discussed during indexing of vectors. So indexing rule will remain similar to those of vectors, that is, we'll be using square brackets for indexing. The only difference now is that we have more than one dimension. So we have to indicate indices corresponding to all dimensions of the array. So that is, if we are using a 2-dimensional array, then we have to indicate the row number and column number. That is the index for the row and index for the column. So that is the only difference. If we are using a 3-dimensional array, then we have to give the row number, the index number for each of the 3 dimensions, as we saw in this particular example that there are 3 dimensions. And if we write it like this, it means the 2 is the index for the third dimension, right? So similar rule will be applied here. So suppose we have already created nn as a 2-dimensional array, numerical array, and if we apply these indexing rules, this is what we'll get. So if I am saying nn12, that means it will return me the value of placed at first row and second column of the 2-dimensional array. That's simple. And if we are writing something like this, nn blank comma 2, so you remember that blank means all the values in, all rows. Blank means all rows, so all rows in the second column. So it will return all rows which have been stored in the second column of the matrix. And alternatively, if I write nn 3 comma blank, then it means 3 is the number for the row, index for the row. So third row and all values and all columns basically. So all values which have been saved in the third row of the array nn, right? So it will return that. So we can see that, we can visualize it here just to show you that what was nn, so that we can relate what is being returned here. So if I am writing nn square bracket, row number as say 3 and column number as 1, so it returns 3 because 3 is the third row and 1 is the first column. So third row first column is nothing but this element 3. And if you want to return the entire column, suppose we want to return the third column. So third column means all the values in the third column, or all rows that is blank, we'll leave it as blank, row index will be blank, comma 3. This is how we write it. So it represents the third column, which is, you can see, which is very easily seen. This is how R denotes the third column as well. So we'll use the same indexing rule here. So when we write that, it simply returns the values 4, 3 and 6, which is nothing but the values which are stored in the third column. And suppose we want to again return all the values in a particular row, suppose. So nn, if I am writing 1 comma blank, that means it will return me all the values which are stored in the first row. So this is nothing but this first row 1 4 4 8. So this is how indexing works in arrays. So a similar rule can be used for more than 2 dimensions as well. You just have to be careful that what index you have to use. And some more examples, suppose you want to do more complex indexing. Suppose here when I am writing nn2 blank 2 to 4, we know that this means sequence 2 to 4, that is 2 3 4. So this is actually same as writing nn blank comma c 2 3 4, concatenate c 2 3 4. This is same, these two statements are same. So what it does is, all rows, blank means all rows, and for which columns? Column number 2, that is this, column number 3 and column number 4. So it will return the columns 2 3 and 4, values in the columns 2 3 and 4. So we can see that. So if I am writing nn square bracket comma, it's all rows, and then say we can use any of the two notations. Either suppose you want to use colon, though you can simply write it like this. So you can see second column is this 4 6 8, it comes first. The third column is 4 3 6, and the last column is 8 9 7. So the three columns, second, third and fourth, have been extracted. But suppose now you want to extract columns but they are not in a sequence, then you can use the concatenate function. You can simply write nn square brackets a comma. So suppose I just want the second and the fourth one, so I can write c2 comma 4. So it extracts only the second and the fourth columns. And similarly you can extract particular rows as well, whatever you want to extract. So all these indexing rules whose foundation was actually laid when we were discussing vectors in detail are very useful. So because suppose, first of all, let me also give you an example for those at least who are not entirely from mathematical background. So why such structures, data structure, or why such arrangement of data in arrays is going to help us, where these things are used. And those from mathematical or statistical background, they know that matrices or arrays are so important that they form the backbone of theory of linear estimation. But for those who are from other background, they can understand it in a very simple way. For example, suppose you are collecting a data on certain number of people, let's say 10 people, A, B, C, and so on. Uh, Suppose there are 10 people, 1, 2, 3, 4, up to 10, and you are collecting data on, suppose, marks in maths, marks in stats, marks in English, and you want to, write this data in a collective format in some kind of structure. So you can use arrays. So the first column, basically, if you define it as an array, the first column will determine the will basically contain the marks in mathematics. The second column will contain the marks in statistics, and the third will contain the marks in English. And each row will represent the marks of each student. So first row will represent the marks in math, stats, and English of the first student. Second row will represent marks in math, stats, and English of the second student, and so on. So this is one way of understanding it. Another way, which is actually very useful, is suppose you are conducting a random experiment on yield of crop, where you have applied different kind of fertilizers uh, in and you want to compare how the yield changes with different kind of fertilizers, right? And suppose each fertilizer has been and suppose there is another factor, which is, say, the kind of seed which has been used. So suppose there are three kinds of fertilizers which have been used, say type A, B, and C, and there are two types of seeds, seed type, two types of seeds which have been used, say type 1 and type 2. So if you enter the data, you can arrange it like an array, you see. So first column will represent, so the data will be yield of crop, say 22, 23 in tons, say 30, 31, 17, 12. So this will represent the yield of crop for fertilizer A, for fertilizer B, for fertilizer C. This single element will represent for the combination of two factors, that is seed type A and fertilizer type seed type 1 and fertilizer type A, and so on. So this is a very useful way. So arrays, or we'll see matrices are just one type of array. So arrays are very useful way of storing data, because this helps us to develop various kinds of mathematical operations, which makes our theory very easy and computations very easy. So anyway, so this is how you can understand the utility of arrays in programming. Now, so we have seen arrays, and now we want to know what are actually matrices. We say arrays and matrices because matrices are simply one kind of array, a specific type of array. So when we restrict our dimensions to only 2 dimensions, and we restrict our type of elements to numbers. So if we are considering an array which is of only 2 dimensions, which is a 2-dimensional array, and it has only numeric values, then it can be called as a matrix, right? So basically, matrix is a type of array, and that's why the indexing rules remain the same as that we discussed for the arrays. So basically, matrices are special kind of arrays where we have only 2 dimensions and the elements can only be numbers. And as I said, that matrices are so useful in mathematics and statistics. All the theory behind estimation, linear estimation, have been developed in form of matrices only, right? So now suppose we want to define matrix. So one way is to use the function array, which we have already discussed. So in array, remember, in the first, as the first argument, we passed the vector of elements which we wanted to assign to the array, and the second was dimension, where we define the dimension of the array. Another way, if we are dealing with matrices in particular, then another function which is available is called the matrix function, and this can be used instead of using the array function if we are dealing with matrices. So here, since when we talk about matrix, we are talking about only 2 dimensions. So now when we define a matrix, the 2 important arguments which we have to pass is, the first one remains the same as that of array, that is the vector of elements which we have to pass to the matrix, and the second one is we can define nrow, that is number of rows. This n means number of rows, or basically we are defining the size of the first dimension, that is row, because we are dealing with only two kinds of two dimensions. That means if we assign one dimension, suppose there are 12 values in x and we are defining that number of rows is 3, then automatically it determines that number of columns will be 4, right? And when we do that, remember that when we were discussing array, we discussed that by default the function assigns the values to the array column wise, that it fills the first column first and then the second column and then the third column and so on. Similarly, for this function as well, the values are assigned column wise by default, but here we also have an option of making sure that the values are assigned row wise instead of column wise. So that we'll see. So first of all, if we are using the function matrix to define a matrix, then again similarly we have to create a vector of elements, or we can define this vector of elements inside the function matrix itself, and then we have to define number of rows, which we can define by the argument nrow equal to whatever the number of rows are there, and automatically then it, based on the number of elements in the vector, it determines the number of columns. Obviously the multiplication of row into column should be equal to the number of elements, so the number of elements in x should be divisible by the number of rows which we are defining, otherwise it will return an error. So here if we define this function like this, then it will create a matrix with name mat1 whose elements are assigned like this. You can see the elements are assigned column wise 1 2 3 and then 4 5 6 to the second column and third column. You can see that the indexing is actually same as that of array, because it is just another array, nothing else, a two-dimensional array, right? So if we want the values to be assigned row wise instead of column wise, then we have to add a third argument to it, which is by row equal to t. You remember t stands for true, so either you can type complete true in capitals or you can simply type capital T, that will be true. So by default by row is false, and if you want assignment to be row wise, then we have to pass the argument by row is equal to true, and then you can see the difference is that now 1 2 3 4 is first row, this is second row, so row wise values have been assigned. You just go back and see the values were 1 2 3 4, then 5 6 8 9, and then 3 4 5 6. So 1 2 3 4 and then 5 6 8 9 and then 3 4 5 6. So row wise assignment has happened, right? So this is another way of defining matrix. Either use array function or you can use the matrix function. So let us define the matrix, because we will be using it for some of the calculations we will be doing later on in this lecture. So suppose I define a matrix, the matrix mat1. No need to use the same values, we can use any. Let's say I define okay, there are 12 values here, I will use the same vector x. So I can use, alright, mat1 as matrix with values from vector x, which has 12 values, and I can write, okay, nrow is equal to 3. Okay. So I run this, and if you want to see the values which are stored here, you see this is how the matrix has been defined or created. And suppose I want to create another matrix 2, what I can do is let me create it row wise. So same values, nrow equal to 3, or maybe let me make it 4 here, and then I want row wise assignment. So by row is equal to capital T. So I'll run it now, and if you want to see how the matrix 2 looks like, it looks like this. So I have given number of rows as 4, so number of columns automatically becomes 3, and by row assignment has been made here, right? So now let's talk about certain functions which are specifically made for matrices, and how to use some other functions like mean, sum, those inbuilt functions using matrix indexing. Suppose we want to apply those functions only on certain columns or certain rows of the matrix, then this is how we can do it. So let's first start with a function which is called dim, and as the name suggests, it is nothing but dimension. So it gives us the dimension of a matrix. So if you have matrix defined and you want to check, because in matrix operations dimension plays a lot of role. We have to check whether some operations are even feasible or not. So if you have forgotten the dimension of a matrix, you want to check it, then you can use the function dimension. So you simply have to write dimension and write the name of the object, that is name of the matrix on inside it, or even name of the array. Actually you can write, it works on arrays and matrices. So you write dimension mat1, it gives similarly dimension matrix 2, it is 4,3. So the dimension of the second matrix is, the number of rows is 4, number of columns is 3, and so on, right? And let's see if it works on arrays. It gives dimension of nn. We had created an array of dimension 3, 4, so it gives us, returns the dimension of the array as well. However, it does not work on vectors. Remember, if I am creating, say you want to apply dimension x, because it is a one dimensional array, it returns null. So instead, if you want to know the length of a vector, there's a function called length. You can write length of x, and it returns the number of elements which are saved in the vector, that is 12 here, right? Again, there is a function I just remembered, which is called class. If you write class and name of the object, say mat1, let's see what it returns. It says it's a matrix or an array, right? And there is another function called str, which is a short for structure. So it returns the structure of an object. So if we want to see what kind of object is a mat1, it gives more information than the class. So it tells us, if I am writing structure mat1, it tells us that it contains numeric values, and then it has 2 dimensions. You see, 1 to 3, 1 to 4 means it has 2 dimensions. The first dimension has 3 levels, the second dimension has 4 levels, and it also gives us some of the values, just as example. If there are few values, it will give us all the values, but if there are more values which are not going to be sufficient in one line, it will just give the first few values to us. So it gives us a general idea about what kind of values are stored, or what kind of structure the object has. So similarly, if we apply str, so say nn, it again gives us the similar kind of, it gives us the size, the kind of elements which are stored there in the array, and which elements are stored there in the array. And if we apply it to a vector, let's say x, again it tells us that numeric values are saved in x, and it has only one dimension, so we can understand that it is a numeric vector having 12 elements, 1 to 12, and these are the elements, some of the elements which are saved. So str is a very useful and class is also useful if you want to see what kind of object something is, because generally you define a lot of objects, sometimes you forget what is the dimension, what kind of values are saved, so you can always do this to find out about them, right? So dimension is a useful function when we are dealing with arrays or matrices. And again we had if you create a three-dimensional array, it will return the dimension of or the sizes of all the three dimensions. Anyways, now there is a function T. For those who know what is a transpose of a matrix, so it returns the transpose of a matrix. So this is an inbuilt function, you can use it. It's simple to see. Suppose we want to find the transpose of the matrix 1, we can simply write T mat1, pass the name of the matrix as the argument, it returns the transpose of the matrix, right? The thing is, if you want to calculate inverse of the matrix, there is a function determinant for determinant, finding out determinant, which is dt. You can see as soon as I type dt, it is defining, the hint has come in RStudio. It says it calculates the determinant of a matrix. So you can simply write dt and pass the name of the matrix. However, those who know what a determinant is, they know that it can be found for only square matrices. So it gives us an error. So suppose I create a square matrix, say M matrix, say the values I take as C 1 to 16 and define nrow equal to 4. So it will be a 4 cross 4 matrix, that is, it is going to be a square matrix. And then if I find determinant, this matrix M, it comes as 0. It comes as 0. It was expected because the rows are linearly dependent on each other. Anyways, that is something different, but this is how you can find determinant. So determinant function is there, transpose function is there, but inverse function for a matrix is not present in the base package. At the last, we will discuss that various packages for matrix calculations, computations are available, and you can use them for even advanced operations on matrices. But we are just dealing with the basics of how to handle matrices and arrays in R here. So, and again, how to use indexing for applying certain functions on specific columns or rows. So suppose we want to apply the function mean only on the second column of the matrix. As I said, that we can have matrices for arranging, say, data, like the first column gives you the marks in mathematics, the second column gives you the marks in statistics, and so on. So if that is so, and suppose you want to see what is the average of marks in mathematics, what is the average marks in statistics separately, that means you have to calculate mean for each column separately. So in that case, this is what you can use. So if we apply this function mean, and then inside we are actually using indexing, so mat1 indexing all rows and second column, that is simply it will give us the mean of the second column of matrix 1. So this is what can be used if you want to apply a function to a vector inside a matrix, or apply a function to a particular row or to a particular column of a matrix. Similarly, here there is an example. If you want to calculate average marks, say for a particular row here, so for the same example, rows represent students. So suppose you want to know what is the average mark of first student, so you'll be calculating the average marks for first row, right? Mean of first row, and so on. So again, this is, I have simply used it as an example. You can use any other inbuilt function like sum or variance or other functions which are available, right? So you can do that. So again, indexing becomes useful in such kind of row wise or column wise operations when we are dealing with arrays and matrices. Uh, Now this is something useful which we are going to discuss, which is attaching or appending rows and columns. Or basically, if you want to combine two matrices and form a single matrix, that is, suppose you had saved marks of certain 10 students in one matrix, and other 20 students in another matrix, and now you want to combine them to create a single data of matrices, single matrix of the entire data of 30 students. So this is what we mean, that when you want to combine matrices to form one, or you can say when you want to append the rows or columns of matrices. So first we are dealing with R bind function, which is R bind is short for row bind. So we are binding rows here. So binding rows means we are attaching rows of one matrix. Say if I am writing row bind mat1 comma mat2, which we have defined matrix 1 and matrix 2, then we are going to attach rows of matrix 2 below the rows of matrix 1, right? So this was actually matrix 1 and this was matrix 2. So this was matrix 1, and what we have done is we have attached the rows of matrix 2 below matrix 1. So number of columns of the resultant matrix, which is a METR, remains the same, that is 4, but now number of rows has increased, which is equal to the number of rows in matrix 1 plus the number of rows in matrix 2. So it is now a 6 row cross 4 column matrix. So when we use R bind, an important thing to note is that the number of columns of the two matrices to be combined should be the same. Otherwise, the operation is not possible. So number of columns for both the matrices should be same. The number of rows can differ. One matrix can have 2 rows, the another can have 3 rows, so the resultant will have 5 rows. But the number of columns should be same for the two matrices. Only then we can combine these two matrices row wise, or we can use R bind from those matrices. So this is an example. If we were talking about that example, that now rows represent students. So that is an example. Suppose first three marks of first 3 students have been saved in matrix 1, and the marks of next 3 students have been saved in matrix 2, and we want to combine them and form a new set of data or new set of matrix. Then we want the marks of all the students. So marks of all the students will be in the 4 subjects, that will remain the same. So number of columns will remain the same, and we can use row bind to create the resultant matrix, right? In some cases we might need to combine the matrices using columns, or combine the columns of two matrices. So in this example we can understand it like this, that in one matrix you have saved the marks for first subject and second subject for all the students, say 1 to 6, and in the second matrix you have saved, say, marks in the third subject and the fourth subject for all these students. So now you want to combine these two column wise, that is, the number of rows will remain the same, 1 to 6. Now you want to add the third and fourth column in the first matrix. So there we can use a function which is called C bind, that is column bind, right? So the next function is nothing but column bind function, and when we want to apply this function, then we have to be sure that the number of rows should match for both the matrices. Then only this operation is possible, otherwise it will show an error, right? So just to show an example here, we have to be sure the dimensions are such that operations are possible. Suppose I want to create a matrix S with R bind and matrix. I'm going to append NN as the first matrix. So even the sequencing is important. Which one do you want to keep first and which one do you want to keep the second, because that will be added to the end of the first one. So NN comma say mat1. I don't remember if the dimensions were same. Let's see. If they are not, then if the number of columns are not same, then it will show us an error. So it has not shown us an error. That means the number of columns in matrix NN and matrix 1 mat1 are same. And let us see what is S. So S, you can see both matrices had only 3 rows, and when we have used R bind, this one was the first matrix and this is the second matrix. Both are basically same. We had used two different functions to define them. We had used array to define the first one, and we had used the function matrix to define the second one, but both were created using the same vector, so they are same. So number of columns obviously is same again, so the function has worked. So it has placed the second matrix, which is mat1, behind the first matrix, which is NN. And similarly you can use, say I define Z using C bind, that is now columns will be combined, so number of rows should be same, and we know that here number of rows are same. Suppose I add matrix 2 here instead of matrix 1. So if I do that, it gives us an error because the number of rows in NN and matrix 2 are not same. But we can do this operation with matrix 1 because the number of rows are same here. And if we see what is Z, you see now here instead of adding columns, this one was the first matrix and the second matrix has been placed after it. That means the columns have increased now. Columns have been appended, or column bind has been operated here, right? So these two functions are also very useful. Generally, if we are working on data and then some new data has come up, we want to add it to the existing data, then we can simply use R bind or C bind to do it if we are dealing with matrices. And some arithmetic operations on matrices. So obviously this plus sign will simply add two matrices. That means it will add corresponding elements of the matrices. This will subtract two matrices or subtract the elements of the matrices. Now this is something important to be, if we use the star sign as operator, then this actually multiplies corresponding elements of the two matrices, and it does not give us matrix multiplication. That is, it does not give us the inner product. So if you want to multiply two matrices, then we have to use this operator, percentage star percentage. So we'll see the difference here. So suppose if I am writing a multiplied by we don't have anything called A. So matrix 1 multiplied by matrix 1. So what it does is, you see, just remember what matrix 1 was, then we can understand what it does. So this is matrix 1. So what it does is it multiplies the corresponding element of matrix 1 with the corresponding element of the second matrix, which is again the matrix 1. So it is 1 into 1, 1. Then this is 4 into 4, 16. 4 into 4, 16. 8 into 8, 64, and so on. So element wise multiplication has happened. But if we talk about matrix multiplication, then we have to use the other symbol. That is, we have to use mat1 percentage, then star percentage, and then mat1. Now you see, non-conformable arguments. Obviously we have to check the feasibility of multiplication. So here actually the size of matrix 1 is 3 cross 4 and 3 cross 4 into 3 cross 4 is not allowed. It has to be 4 cross 3. So let us use the function transpose. So suppose I create M as T of mat 1. Now I can multiply matrix 1 with M. So you see matrix multiplication. So matrix 1 was 3 cross 3, M is 3 cross 4, M is 4 cross 3. So the resultant matrix is a 3 cross 3 matrix. So this symbol, remember, if whenever you have to use matrix multiplication, instead of simply using star, you have to use percentage star percentage, right? Now what about other advanced operations in matrices? So the base packages which are there in R, pre-installed in R, they do not have, they even do not have a function for direct function for calculating inverse. So if you want to calculate inverse of a matrix, or if you want to find eigenvectors, or even higher operations as generalized inverse, and all those things, and much complex operations are available in very specialized packages. I have just written two of the names of two names which I know, but I'm sure that there are various other packages available in the CRAN library. You can check. So one is matrix, which is very popular, and another is matlib. And if you want to know anything about these packages and how are they used, obviously all the uh, helps, all the manual about these, about the functions are available in the CRAN. So for example, you can just go here. If you just search for, say, matlib package in R, it will come. Open the CRAN one, and you can see this is all the details which are there about the matlib function. So here you can see reference manual is there, matlib, and it contains details about the package and all the functions which are available, and examples of these functions are shown. For example, for inverse, it has a function. Let me just check if I remember rightly. Yeah, inverse, called inverse itself. If we go there, there is a function called inverse, and it gives details of the arguments which are passed in the function. So x is passed, which should be a matrix, right? And then it gives some examples as well. You see a matrix A has been created and inverse of the matrix can be found. But if you want to use this package, since I have not shown you how to download packages for those who are beginners now, so let us say we want to use the function matlib because we want to use inverse function, which is not there in the base package. So if you are connected to internet, you can just write install dot packages and then write the name of the package, matlib, and then press enter. Sorry, install packages, matlib. I have the name is, yeah, I didn't use the double quotes. You have to use the double quotes. You see, if the internet is working, the computer is connected to the internet, then it will download the package automatically. So remember the function install.packages. So it will install it, and then I'll show you how to use it after installing it. See, all the packages which are pre-installed in R, the base packages they are already there in the library, and whenever you run R, you can use all the inbuilt functions directly which are present in those libraries, in those packages. However, if we are downloading an additional package like this, which we have downloaded, matlib, and it is being installed right now. So after it is installed, whenever we want to use it for any session of R, we have to add it to the library. Then only it will we will be able to use the functions which are defined in that package. It is taking some time. It's a very complex package. Yeah. So let us just wait for it to be installed. So actually a lot of other packages which are used in this package are also installed in the process. Yeah. So that's why it is taking time. Some packages take a very little time to be installed. Some are yeah, much more complicated and size-wise huge packages, so they take time. So it has been, now you see the download source packages have been installed, downloaded and installed. So now if you want to use this downloaded package, say if we saw that it has a function inverse, so if I write inverse of mat1, so inverse we are talking about uh, I had defined one square matrix. We need to talk about square matrices when we are talking about inverse. So where is it? Okay, I don't remember. So let me just define a square matrix so we can use the function. So I had used, okay, I'll define a new function here. Mat matrix C 1 2 say 1 4 7. Okay, and nrow is equal to 3. So I'm defining a 3 cross 3 matrix. So you can see it's a 3 cross what happened? I'm defining a 3 cross 3 matrix here, auto correction. Defining 3 cross 3 matrix like this. So now we can, suppose I want to use the function inverse. I've installed the package matlib, but it will not work. You see, it will say that the function matrix, the auto function is, yeah. So it says error, could not find the function inverse because we have not added that package to the library. So we have to use the library function, library, and then we have to write the name of the package matlib. So library matlib, either you can write it like this or you can use matlib. So using this, what happens that we have added the package matlib to this session, to the R session, to the library of the R session. So now the functions available in matlib package can be used. So let's see now if the inverse function is working. You see now the function inverse which is there in the package matlib is working. It has returned the inverse of the matrix mat, that is mat, right? So this is how you can explore all the other functions which are available. Those who use high higher mathematics of metrics, they can use these packages and explore these packages even more. So that's all for today's lecture. Thank you and take care, and I hope you have learned something new today. Okay.